This video is a quick review of the first principles of physics that apply for calculating the Hubble constant. Okay, so here we go. As space expands, here we're using the well-known balloon analogy, the distance between objects that are like the Earth and the distant galaxies also expand, even though their positions on a co-moving coordinate system remain the same. There are things like meter sticks, clumps of matter held together by electromagnetic or electrostatic or electroweak forces, the length of which does not increase appreciably as space expands. Another example would be a bunch of stars in a local galaxy where their relative positions are being held together by gravity. As space expands, that group of stars, other than local velocities, remain more or less at the same distances from each other. Now, the third thing to review is that light represents a packet of light, represented here by its wavelength over some distance in space. As the space expands, the wavelength of the packet of light does expand. It gets longer, which is the cause of the cosmological redshift as a result of the expansion of space. This diagram will help to dispel some of the myths that widely circulate about what's being measured as far as the distance to the distant galaxies. If this is the Earth and this is a galaxy, if we measured the distance by laying out meter sticks all along the path, then when light is emitted from the galaxy for the first little while, space hasn't had time to expand very much, so the space is still more or less the length of 1 meter stick. As the light travels towards Earth, each unit of space has more time to expand more and more and more as light travels towards the Earth, which leads to a picture like this. Here's the photon packet when it left. Here's the photon packet when it arrived. Here's the sum of all the distances that it traveled through to get to the Earth. That's the distance dl, and that is the distance that astronomers and cosmologists measure when they calculate the distance that they observe of the light on Earth. And that applies to visual light, red spectrum, microwave observations, whatever. What's being observed on Earth is the light at the end of its travel through all of this distance, which leads to the calculations. And it's immediately obvious that the distance that the light traveled is much larger than the distance that the galaxy was from the Earth at the time the light was emitted. So it's incorrect to say that the measured distance is the distance to the galaxy. It wasn't the distance when the light was emitted, and it's not the distance when the light is observed, because when the light is observed, each of these segments will have expanded by the maximum amount. So the picture would be segment, 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 with a galaxy off the edge of the page here somewhere. Now, these diagrams are addressing the recessional velocity between the Earth and the galaxy, and whether or not that gives rise to a Doppler redshift that also plays a role in the observed redshift of the light on Earth. So Okay, basic expansion of space, Earth, galaxy, time equals 0, Earth, galaxy, certain distance apart. As time goes on, they get farther and farther apart. The meter sticks show that they're getting farther and farther apart. Over here we have any other two objects in space, like the Earth and a spaceship, where the spaceship is traveling away from the Earth. Over time, the spaceship gets farther and farther from the Earth. At this point in time, the spaceship sends a radio transmission or a beam of light back towards the Earth, which arrives down here. This beam of light is obviously redshifted due to a Doppler effect, and the velocity, the recessional velocity between the two objects is change in distance over the change in time. Now, both of these diagrams could be shown from a frame of reference of the Earth where it's not moving, and in both cases the other object has, relatively speaking, a recessional velocity. So I've drawn that as V1, V2, and V3. So from these first principles we can see that there would be a Doppler redshift from the galaxy, a Doppler redshift of the light emitted at time equals 0 when it's received on Earth, because of the recessional velocity at time equals 0 of the galaxy relative to the Earth. And the ordinary equations of the special theory of relativity or the non-relativistic Doppler shift equations would apply for that component of the redshift. Now, are there any other reasons why this analysis should not hold true for a distant galaxy and the Earth, and why the special theory of relativity would not apply in analyzing that in the case of a distant galaxy and the Earth? Well, two reasons are sometimes given. One has to do with co-moving coordinate systems. The other has to do with general relativity. And those are discussed in the next segment.